All right, good morning, troops. How is everybody today? Let me get this thing adjusted here. How's that? All right, hey, how we doing, guys? Hope everyone's having a good day. Today is Wednesday, and we are going to be doing a couple things on defining an atom. So, if you guys would, we worked on a little study guide the other day with defining an atom, and I'm going to flip this camera around here so that you guys can see what is going on and what you guys need to get out. So if you guys would get out the Chapter 4 study guide, and it looks like this. It starts out by looking like this. So what I need you guys to do is now turn to the back of this to like number 24. Our goal one day was 23. So all I need you guys to do is look at number 24. It says the mass of an electron on number 24 is smaller than the mass of a proton A, B, smaller than the mass of a neutron, or C, a tiny fraction of the mass of an atom. Well, the mass of an electron is all the above. Okay, and on number 25, the atomic mass unit is also carbon, that 1/12 that mass of the carbon atom. So what that is, if you guys look on your periodic table, carbon is set up in a way here that the total mass is 12, which means that this was the center of how all of the elements were going to be set up, and that is its basis on the periodic table being set up. The atomic mass, number 26, of an atom usually is not a whole number. Okay? The atomic mass is usually not a whole number because it accounts for both the relative abundance and the mass of each atom. Now, I'm going to show you guys how to calculate the relative abundance by doing this problem 33 together. Now here we see X with a mass of 35, and we see a mass X of 37. Now what you guys need to do is X's mass, which is 35, has an AMU called atomic mass units of 34.969. Its abundance, or how much it occurs, is 75.77. The isotope X37 is going to be 36.966 mass, and it occurs 24. Now, hopefully you guys see that this adds up to 100%, so our end should also be 100%. So we are going to actually see how all of this contributes. So what you're going to do is you're going to take the mass of X and 35, 34.969, and you're going to multiply it by, now remember this is a percentage, so it's 0.7577. Now, if you take the old trusty phone calculator, okay, you take 34.969 times 0.7577. Boom! 26.49%. Oh, I'm sorry, 26.49 grams. So 26.49 is how much this contributes at this percentage. So on the other one, you take 36.966 times 0.2423. So let's take 36.966 times 0.2423, and we get 8.95 or 8.96. 8.96. Now, that brings us to wanting the total mass here. So if we take that number, 8.96, plus 26.49, we get an average mass of 35.45. Okay? Now, if you guys look back on the periodic table, what element has a mass of 35.45? 10, 12, 14, 16, 19. Uh-oh, look here. 35.45. So our unknown element, which has an isotope of 35 and 37, 35 and 37, is chlorine. That is our unknown isotope. Alrighty, troops, I'm back. So, what you guys need to be looking at is your pink sheet, the 3-4 practice problems, and what this is going to do is it's going to allow us to look at alpha and beta decay. Now, what this is going to resemble is that of radiation decay or radioactive decay. Okay, radioactive decay. Now, when things decay, they're just going to break down. So that's what we're going to do with the atom here. We are going to literally break it down. The strongest type of radioactive decay that we have are called gamma rays. Now, when you guys look at gamma rays, these are going to be very, very strong, and they can only be blocked by a lead shield. So if you guys go to the dentist or go to the doctor, or girls, even though you get that question asked of you, is there any chance that you guys could possibly be pregnant? Then you have to say that because gamma rays will penetrate the stomach or skin and into body tissue. So they are the strongest. So that's why they put a lead vest over you at the dentist office to block that out. The next type of radioactive decay that we have is going to be a beta particle. Now, these aren't as penetrating as gamma rays, but they are the next strongest. They can be blocked by heavy sweatshirts. Or coats. Their signal here is, whoops, that's alpha, is a beta particle. Gamma is upside down like that. And then finally we have alpha particles. Now, you guys have heard of alpha particles or alpha radiation from the gold foil experiment. This is what he shot into the ring with the gold foil, and that is what we determined that we had a positive mass in the center. This is what we are going to actually work with, as well as a beta particle for decay. Now, if you flip to the front, it says write a nuclear equation for the alpha decay of 23191 Pa. Now, an alpha particle is going to be that of what we call a helium particle. So it is going to have the same setup, a mass of 4, proton of 2, and it's going to resemble a helium particle. We are also going to write this just like that. Okay. A beta particle is going to resemble that of an electron. So electrons don't have a mass, and they have a charge of -1. So these are the symbols that we are going to use for alpha and beta decay. So if you flip to the front, It says write a nuclear equation for the alpha decay of this. So when you go through an alpha decay, I want you to put 4 over 2, just like this. Now, what is 231 minus 4? That's right, 227. Very good. What is 91 minus 2? 89. Now, what do we know about this element? If you look on the periodic table, element 89 is going to be in your bottom right hand corner, actinium, AC. So then you just write its element symbol there, and that's what it is. So it's basically 231 minus 4 is 227. 91 minus 2 is 89. Now what this is going to do is it's going to allow you to have that alpha decay. Now let's do a beta one real quick before I run out of time here. 198 over 85. Now beta decay is 0 minus 1. And what is 198 minus 0? That's right, still 198. What is 85 minus a negative 1? It's going to be 86. So you actually add 1, and going back, 86 on our periodic table is that wonderful gas that we find in basements called radon gas, Rn. So as beta decay happens, you actually keep the same mass and you actually add the electrons. Okay? So all you have to do is follow those two examples to complete alpha and beta decay. Now this is also going to resemble what you see in the book, and the sub will give you those pages that you need to cover and read and be responsible for. But at least this gives you a little insight as to how to calculate and write a chemical reaction that deals with alpha decay and beta decay. Hey troops, you guys have a quality day, and I'm going to go ride some roller coasters. Later.